All right, it's time for the very important fundamental theorem of algebra. If a polynomial has degree n, where n is a number that's at least 1, a polynomial of degree n has at least one complex zero. That's the formal statement of the fundamental theorem of algebra. However, it has other implications because as soon as we find one complex zero, we have now seen that we can turn that zero into a factor and factor that out of the polynomial, leaving us with a degree n minus 1 polynomial. Then we could apply the fundamental theorem of algebra again to that degree n minus 1 polynomial. And so by an iterative process, we could then show that every degree n polynomial has exactly n complex zeros, multiplicity counted. And we're going to see exactly what that multiplicity counted means. Also, we can see that a degree n polynomial can be written as a product of n factors when factored over the complex numbers, noting that these factors are not necessarily distinct. What that means is if we have, for example, a multiplicity 2, 0, well, that's going to correspond to a squared factor. We would count that squared factor as 2 factors for the sake of the fundamental theorem of algebra. So what we're going to do is apply that to this graph that we see, a graph of a polynomial, and see if we can answer all of these questions about it. Some of this is going to go back to earlier lessons. The first thing we want to do is guess the degree of the polynomial we're looking at. It has 1, 2, 3, 4 turning points, so we know that the minimum degree is 5. We're going to assume, for the sake of these exercises, that the polynomials we're looking at have the minimum degree. So we're guessing this is a degree 5 polynomial, and that's consistent with what I see in the end behavior, because that definitely is two ends going in opposite directions, which is what I should see for an odd degree polynomial. The fundamental theorem of algebra tells us this part right here, which is the number of complex zeros. That must equal the degree. This is the theorem that we just saw. So we're talking about multiplicity counted, which means that if we had a zero of multiplicity 2, that would count as 2 zeros toward the fundamental theorem of algebra. Now, counting the real zeros, again, including their multiplicity, we are looking for x-intercepts. First, we have an x-intercept here where the graph simply crosses, right? It crosses just like a linear function would cross the x-axis. So this is a multiplicity 1. This is a multiplicity 1, 0. The other 0 we have, if we look at it locally, it looks a bit like the graph of y equals x squared. It touches the x-axis but turns back around again. This is a multiplicity 2, 0. So counting up our zeros, including the multiplicity, we would say that 1 plus 2 equals 3. So we have 3 real zeros multiplicity counted. Now, the way that we calculate the number of imaginary zeros is like this. We have 5 complex. We subtract off the 3 real to find that we have 2 remaining. And those are our imaginary or non-real zeros. They may not be pure imaginary, but they are at least zeros with a non-zero imaginary part. Looking at the graph, we can also see those imaginary zeros showing up in another way. If we start from the left and just follow this graph, right? We know that the way to get the maximum number of real zeros is if every time we turn around, we also cross the x-axis. Well, here I can see that the graph turned around without quite reaching the x-axis. And we saw in a previous section that that would take away 2 of my potential real zeros. If I have a turnaround here that doesn't quite reach the x-axis, I lose 2 of my potential zeros. So that's a loss of 2 real zeros, that's a gain of 2 non-real zeros. Then I see that here I turned around while touching the x-axis. That was a loss of 1 potential real zero, except for the fact that when we're counting multiplicity, it really isn't. We don't lose that because it counts as 2. So touching the x-axis really doesn't have any effect at all on the number of imaginary zeros. But back over here, where the graph turned around without touching, that was a loss of 2 potential real zeros. That was a gain of 2 non-real zeros. So we can look at the graph and in pairs of 2 find where those non-real zeros would be coming from. Looking at this second example, we're going to start by just analyzing the graph and seeing if we can guess the number of non-real or imaginary zeros first. Here I can see a dip in the graph that did not quite reach the x-axis. Here I can see another. So my guess might be, for starters, that we have 2 pairs of non-real zeros. Remember that they come in these conjugate pairs. So we're always going to get a multiple of 2. You can't possibly have 3 non-real zeros. So let's do the math and see if it all works out. This looks like a degree 4 polynomial, which I can tell from the fact that I have 1, 2, 3 turning points. So remember, the number of turning points is generally 1 less than the degree, which tells us that the degree in this case would be 4. And the number of complex zeros is the same as the degree, because that's what the fundamental theorem of algebra tells us. So these are always the same. Now, the number of real zeros, this graph does not cross or touch the x-axis at all, so I have no real zeros, and therefore I'm going to get, for my number of imaginary zeros, the number of complex zeros minus the number of real zeros, which gives me, indeed, 4 non-real or imaginary zeros.